Hello again, welcome to Hi-Hat, Devlog number 3. My name is Carter Anderson, and today we're going to be covering artificial intelligence and rendering. Up until this point, Hi-Hat's AIs were basically dumb as rocks. They had no awareness of the platforms they were on, and they would happily walk off to their deaths. They also had no ability to jump between platforms, and they had no awareness of the stage's layout. I finally found some time to do AI the way I wanted to. This consists of two major systems, the platform graph and behavior trees. The platform graph is what AIs will use to navigate the stage. The nodes in the graph represent points on platforms. The red edges connect nodes that are adjacent to each other on the platform. I call them walk edges because the AIs can walk between them. These green edges connect nodes that players can jump between. These are calculated by casting rays that approximate the player's jump. This uses the exact same movement code that the player controller uses, which ensures that the jumps line up. Multiple jump patterns are tested, with different initial speeds, number of jumps, and delays between jumps. If one of the raycasts hits a platform collider, a new jump edge is added and its parameters are recorded. These parameters will later be used by the AIs to perform their jumps. I also made the platform densities configurable. Higher densities increase the accuracy of the graph, but they come at the cost of higher initial creation times and more expensive pathfinding during the game. The graph generation system is dynamic and will adapt to any stage you throw at it. Alright, next up we have AI behavior trees. AI code can get complicated pretty quickly. Behavior trees help manage this complexity by breaking the code up into small, reusable components. Each node in the tree corresponds to a single behavior. Execution starts at the top and works its way through the tree in a predictable manner. There are many different ways to go about building trees, but I opted for a code-first approach. I define behavior nodes in code, I link them together, and then at runtime you can view them with Visual Debugger. Each node in the tree returns a status when it's done executing. These can be success, failure, or still running if the work hasn't been finished yet. To illustrate this, here's a simple pickup behavior that I implemented for Hi-Hat's AIs. The run all node is an entry point, and it simply runs every child node. Sequence is a little more complicated. It attempts to run its children in order. If the current child returns success, it moves on to the next child. If it's still running, that node will pick up where it left off on the next execution, and if it failed, the full sequence will start over. The first child is a timed node. This will register as running for a configurable period of time, and return success when that time has elapsed. The next child is the pickup action, and it simply attempts to pick something up, returns success when that happens, and returns failure when it doesn't. When combined together, these nodes result in a behavior where the player attempts to pick something up once per second. This next one is the pathfinding and movement behavior. This is where the platform graph we discussed earlier comes into play. From a high level, this behavior does a few things. It periodically updates the current target. This can either be a player or an item. It checks to see whether the current path should be updated, and it follows the current path. This uses the A* pathfinding algorithm. The player simply walks across walk edges. Jump edges are traversed using the parameters recorded in each jump edge. In the A* algorithm, walk edges have a lower cost than jump edges, which means the player will give priority to walking on the current platform to jumping to a new one. This is a good idea, because jumping across platforms is much riskier than walking across solid ground. This is the jump to safety behavior. With this, AIs periodically cast rays to see if they're falling to their deaths. If they are, they will attempt to save themselves. This is done by testing multiple jumps using the same raycasting technique I used in the platform graph. When a jump test hits a platform, the player uses that jump test's parameters to perform the jump. And here's the whole behavior tree in action. Hopefully it makes a bit of sense now. I love how the system at a glance lets me determine why an AI made a decision. And I no longer have to worry that extending my AI will make the system a rat's nest of interrelated code. The skyscraper stage was looking pretty empty, so I decided to spice it up a little bit with some props. When players take damage, they now emit stars to indicate the damage was taken. Fast-moving players now have a speedline shader to accentuate their speed. This is especially prevalent with bunny ears, but you can also see it when you're falling or if you're hit really hard. Players now have a shield which protects them from attacks. It slowly recharges over time. Shields also protect your hats. Shield charge is shared across all hats and the player. Stolen hats now turn the color of the thief. They also have a new trail effect. Dropped hats now bounce off platforms they hit and start homing in on the player that dropped them. This enables some really interesting movement patterns that I think players will find freeing. This may be controversial, but I added health bars to the players. They go down when damage is taken, and they're reset when you fall off the stage. I added this because it seemed like players didn't have enough incentive to actually deal damage to each other. This was especially true in the early game. The less health you have, the more a hard hit will affect you. Notice how this player with full health takes almost no knockback, whereas this player with low health gets knocked back significantly. Player statuses are now scalable, both in the horizontal and vertical directions. Statuses now also hide themselves when they're obstructing important stuff, such as players or items. I made this sword slash effect to make the knight helmet attack a little more satisfying. I recorded the process I went through to make this, and you can view it on my channel. So I removed AI's right to vote. They no longer have a say in pre-game selections. I just hope our future AI overlords don't remember this. Up until this point, Hi-Hat used Godot's modern OpenGL ES3 renderer. This had some pretty effects like screen space ambient occlusion and multi-sample anti-aliasing, but there have been many reports of it running poorly on older hardware, and in some cases not even running at all. I want to enable everybody to enjoy my game, so I migrated to Godot's less fancy OpenGL ES2 renderer. It looks less pretty, but it has much wider hardware support. The OpenGL ES2 renderer currently doesn't have any anti-aliasing support, so I ported NVIDIA's FXAA implementation to a Godot shader. You just add the node to any scene, and it instantly has nice anti-aliasing. It is worth pointing out that multi-sample anti-aliasing support in the OpenGL ES2 renderer was recently merged into the Godot master branch, so it will probably land in the Godot 3.2 release. And that's basically it for now. I know I've been saying this a lot, but I really want to get this in the hands of some testers. I think the game is in a place where feedback from other people is important to determine its next direction. The best ways to hear about testing opportunities and other Hi-Hat updates are to subscribe to this channel and follow me on Twitter, which I will link to below. I want to personally thank everybody who's engaged with Hi-Hat so far. I never expected that this game would resonate with people as much as it has. I'm glad there are other people out there that share my wonky sensibilities. It really warms my heart. You all are awesome.